In this video, I want to introduce you to the Lagrange polynomial, which can be used to construct interpolating polynomials when we have unequally spaced data. An example of unequally spaced data would be something like this. We have the x values given here, and we have the corresponding y values or the f values here. And if you see the gap between the first x value and the second x value, the first x value is indicated by x naught, the second x value is indicated by x1 in this particular table. You see the gap is 0.2 between 1.2 and 1. If you look at the gap between the second and third data points, the gap between x1 and x2 is 0.3. And then the gap between x3 and x2 is 0.1. So we have data from unequally spaced x measurements. In this situation, the Lagrange polynomial is a very useful one. And the idea is fairly simple. The Lagrange polynomial is very useful for unequally spaced data. The data is denoted by this pair xi, fi, and I goes from 0 to n. So the first data point would be referred to as x0. The corresponding f value will be f0. That will be the symbol that's used. And so on. The last data point is xn, and the corresponding value of f is fn. So totally you can see there are n plus 1 data points. Now, the Lagrange polynomial Pn of x is defined by the summation. I goes from 0 to n. So there is actually going to be n plus 1 terms on the right hand side, which we can write it as f naught delta naught x plus f1 delta 1 x and so on till fn delta nx. That's what the summation expands to. So Pn of x will have n plus 1 terms on the right hand side. What is this delta I of x? We have used delta I of x here. So I goes from 0 to n. So what is delta I of x? It's given by this product, right? So this symbol means it's a product. Like this symbol means it's a summation, and the product goes from j is equal to 0 to n. So the product would have n plus 1 terms, but interestingly, j cannot take the value I. So it can go from 0 to 1 to 2 to I minus 1. Then it skips to I plus 1, I plus 2 all the way till n. And you can readily see, since the right hand side is going to be a product of n terms, delta ix for any I will be a nth degree polynomial, because this by itself is a first order polynomial, x minus xj. And if you have n such terms, you're going to raise it to the power of n. So every delta ix, delta 0x, delta 1x, delta 2x, delta nx, each of them is going to be a nth degree polynomial. The denominator is just a numerical value, but the numerator is a function of x. So xj is a numerical value, xi is a numerical value, but x is a symbol. So delta I is a function of x, and the right hand side will be a polynomial of nth degree. So basically what you're doing is you're constructing several polynomials of nth degree. Each of them are nth degree, but they are not the same. They are different, but each of them are nth degree polynomials, and you multiply each of them by weights. The weights are f0, f1, f2, fn, which are the values of the dependent variable. So the measurements of the dependent variable f0, f1, f2, fn serve as weights for each of those delta polynomials, each of which is of order n. Before moving on, I want to clarify one of the other properties of this delta I polynomials. When the delta I polynomial is evaluated at x is equal to xj, so delta I xj, then the result is 0 if j is not equal to I. So if you are looking at delta 1 x2 or delta 3 x4 or delta 4 x3, all of these are going to be equal to 0 because I and j are different. So this is going to be the case. So you can look at it, right? Instead of x, you put xj here, and xi is not equal to xj. All right, that's the condition here. If j is not equal to I, xi is not equal to xj. So under that condition, if you put x is equal to xj, we are going to get xj minus xj. And since it's a product, if even one numerator goes to 0, the whole product goes to 0. So we understand why it might be 0 here. But let's look at a condition where I is equal to j. That means we are talking about delta 1 evaluated at x1 or delta 2 polynomial evaluated at x2 and so on. Here I is equal to j. So when I is equal to j, x can be replaced by xi. So xi minus xj divided by xi minus xj, that will give you equal to 1. So this delta I evaluated at xj equals 0 when j is not equal to I, and it is equal to 1 when j becomes equal to I. So this is something like the Kronecker delta function, which is alive at only one point and it is 0 at all other points. Now let's look at a case where n is equal to 2. If n is equal to 2, we know we have data points x0, f0, x1, f1, and x2, f2. So 0, 1, and 2. So there are three samples or three data points or three data pairs if you like. So we are going to talk about P2 of x. So P2 of x is going to be equal to f0 times delta naught x plus f1 delta 1x plus f2 delta 2x. This comes from this definition. What is delta naught x? Delta naught x is going to be the product for j is equal to 0 to n. So j is equal to 0 to 2, n is 2, and j should not equal I, and I is 0 in this case. So j should not be equal to 0. And this is going to be x minus xj divided by xi minus xj. That comes from this definition. So when you evaluate this, this is going to be, you should start from j is equal to 1. Though the product goes from 0 to 2 for j, j should not be equal to 0. Therefore, you start from j is equal to 1. So this is going to be x minus x1 divided by x0 minus x1 times, then j becomes 2, x minus x2 divided by x0 minus x2. So that is delta 0x. So that is what we have here. This is delta 0 of x. So f naught delta naught of x. And as you can see, x0, x1 and x2 are given numbers, but the numerator is a second order polynomial in x because you have x minus x1 multiplying x minus x2. So this term is going to be a second order polynomial in x. And that meets what we set out to find out, P2 of x. Now, when you come to the second term, it is going to be f1 delta 1x. So here I is equal to 1. So delta 1x will be equal to the product. J goes from 0 to 2 and j should not be equal to 1 because I is equal to 1 here in delta 1x. So this is going to be x minus xj divided by xi minus xj. So you have to start at j is equal to 0. So we are going to have x minus x naught by x1 minus x0, because I is equal to 1 here. We are looking at delta 1. So this is the first term. Then j becomes 1, but j cannot be equal to 1 by definition. So we skip that and go to j is equal to 2, in which case it is going to be x minus x2 by x1 minus x2. So this is delta 1. X minus x0, x minus x2, x1 minus x0, x1 minus x2. So that is delta 1. So f1 multiplied by delta 1x. Likewise, you can do this and show that delta 2 is going to be this. And delta 2 multiplied by f2 gives the third term on the right hand side. So what we have done is we have used these basic definitions and we have set up for a system with 3 data points. We are setting up a Lagrange polynomial of order 2. Note each of these terms is of order 2. Now this will pass through f0, f1 and f2. That means that it's an interpolating polynomial. Why? Because if you put x is equal to x0, this term will drop off, as you can see, because you're going to have x0 minus x0. When x is equal to x0, this term goes away, this term goes away, because if x is equal to x0, you are going to get x0 minus x0 here and here. So these two terms will become 0, and this one is going to become x0 minus x1 multiplied by x0 minus x2 divided by x0 minus x1 times x0 minus x2. So the numerator and the denominator will be the same. Therefore, you will have only f0. So at x is equal to x0, p2 of x is equal to f0. Therefore, the polynomial p2x as written here passes through f0. Similarly, when x is equal to x1, this term will go to 0, this term will go to 0, only this term will survive. And when x is equal to x1, this term will be equal to 1. So p2 at x1 is going to be f1. Therefore, p2 of x passes through f1 perfectly. Likewise, we can show that when x is equal to x2, only the last term survives and even the last term simplifies to f2. So p2 at x is equal to x2 will be equal to f2. That means p2 of x passes through f2 also perfectly. So it's a interpolating polynomial. Next, we can say that we would be able to write this p2 of x as p2 of x is equal to some a0 plus a1 x minus x0 plus a2 x minus x0 x minus x1 for some a0, a1 and a2. We need to find out what would be the value of a0, what would be the value of a1, what would be the value of a2. Why do we make this claim? We make this claim because each of these terms is a second order polynomial in our example. And this is also a second order polynomial. For some relationship between a0, a1 and a2 and f0, f1, f2, x0, x1, x2, these two things would be exactly the same. We can show that. In fact, if you have time, pick up a pencil and paper and expand these terms that you see on the right hand side of p2 of x. You would be able to put it into this particular form. Do not be worried that x2 is not showing up here, whereas it is showing here, right? You see x2 in many places here. x2 will actually feature in a0, a1 and a2, somewhere there. x2 will appear. So there is a strong equivalence between these two representations of the second order polynomial. In fact, we can generalize this further and say, if you write a Lagrange polynomial Pn of x, we can show that it can be expressed in this particular form as Pn of x is equal to a0 plus a1 times x minus x0 plus a2 times x minus x naught into x minus x1 plus 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 all the way till an x minus x naught, x minus x1, x minus x2 all the way till x minus xn minus 1. Please note the order of this term is going to be x to the power of n because you have x minus x naught that will give you x to the power of 1. Then you will have x minus x1 which will give you another x to the power of 1. So if you have two terms, you have second order polynomial. If you have n terms like this, please note we are starting at 0 and ending at n minus 1. So if you have n terms multiplying, this term is going to be a polynomial of order x to the power of n. The previous term would be of the order of x to the power of n minus 1 and so on. This term will be of the order of x to the power of 1. This term would be of the order of x to the power of 0. So Pn of x written in this particular way is also a nth order polynomial. Pn of x written in this particular way as Pn of x is equal to f naught delta naught x plus f1 delta 1x plus fn delta nx, where delta naught, delta 1, delta n are all polynomials of order n. This is also a nth order polynomial. This is also a nth order polynomial. So these are just two representations of the same thing. So let me just summarize what we did so far. We defined something called a Lagrange polynomial that takes this particular structure, where each term is of the order of n in general. Each term is the nth order polynomial, and you add n plus 1 of those polynomials, and the result will also be a nth order polynomial. The nth order polynomial can also be written as something like this. Pn of x is equal to a naught plus a1x plus all the way plus an x to the power of n. This is also a polynomial of order n. Yet another way you can represent the polynomial of order n is like this. The advantage of this representation is that at x is equal to x naught, only a naught will survive because this term will become x naught minus x naught, so this will go to 0. This will also die at x is equal to x naught because you have x minus x naught term. So all the terms has this x minus x naught term. Therefore, at x is equal to x naught, only a naught will survive. And at x is equal to x1, this term will survive, this term will survive. This term will die because it has got x minus x1, and when x is equal to x1, this will become 0, making this whole thing 0. And after this term, all the terms will have x minus x1 in there. Therefore, all of them will go to 0. So at x is equal to x1, only the first two terms will survive, and you will get Pn of x1 is equal to a naught plus a1 x1 minus x naught. And Pn of x naught is only going to be a naught. And Pn of x2, right, the polynomial evaluated at x is equal to x2 will have only these terms, a naught plus a1 times x2 minus x naught plus a2 x2 minus x naught times x2 minus x1. All the other terms will drop off to 0. So this representation has certain advantages. So it is all the same thing. Only the manifestations are different. So in any case, what is important for us is to acknowledge that this is a Lagrange polynomial. This is the way of representing the Lagrange polynomial. This is the way we would like to represent it ultimately, and therefore we are trying to seek the connections between this and this. That means, what's the value of a naught? what's the value of a1, a2, an that will make this representation the same as this representation. So that is where we are headed towards. So in order to make progress and develop compact forms, we will introduce this concept called divided differences. You can take this as definitions and agree that this is a kind of an algebra. So the first divided difference, DD means divided difference. The first divided difference is denoted by the symbol F in square brackets x0, x1. That is equal to f1 minus f0 divided by x1 minus x0. So this is what f x0 x1 is, the first divided differences. So if you were to write f x1 x2, we would go f2 minus f1 divided by x2 minus x1. All right. So basically it's like the derivative, the change in the function divided by the change in x. All right. So it's an estimate of the slope, if you like. It's an estimate of the slope between data pairs x0, f0 and x1, f1. Now, after we know how to define the first divided difference, we can have the definition for second divided differences. And that is something like this. So f x0, x1, x2. So for the first divided difference, you will need two symbols inside the square brackets. For the second divided difference, you will have three symbols in the square brackets. So the second divided difference involving x0, x1 and x2 will be given by this expression. So very much like what you see here, f of this minus f of this divided by this minus this. So there is some kind of a pattern between the first divided difference and the second divided difference. The second divided difference uses the first divided difference. So if I expand this second divided difference, what is f x1, x2? It is going to be f2 minus f1 divided by x2 minus x1. So that is this minus what is f x0, x1? The first divided difference involving x0 and x1. It is going to be f1 minus f0 divided by x1 minus x0. So this is the first term. This is the second term. And then the whole thing should be divided by x2 minus x0. So it is the divided difference of the first divided difference. So it's like the second derivative. All right. So this is the notation for divided differences. And you can keep going forever. You can have a third divided difference involving f x0, x1, x2, x3. You can write it as f x1, x2, x3. The second divided difference involving x1, x2 and x3 minus f x0, x1, x2, the whole thing divided by x3 minus x0. This would be the third divided difference. Of course, you can expand this and you can expand this in terms of the first divided differences. And then you can expand the first divided differences using the basic data points. So ultimately, the first divided difference, the second divided difference, the third divided difference, All of them are going to be a bunch of numbers that are obtained from the tabulated data that is given to us. So with this background, let's proceed further. Now, what is Pn at x naught? Pn at x naught is going to be a naught. We saw this earlier. Pn at x naught, all the other terms are going to be 0 at x is equal to x naught. So therefore only this term will survive. Therefore Pn at x naught is going to be equal to a naught as discussed earlier, and we can just represent it as f at x naught or just f naught. Why do we say this is equal to f naught? Because when x is equal to x naught, this term will go to 0, this term will go to 0, leaving us only with the first term, and when x is equal to x naught, the first term will reduce to f naught as we discussed some time ago. So P2 at x naught from this expression is going to be f naught. P2 at x is equal to x naught from here is going to give us a naught. Since we are talking about the same interpolating polynomial, a naught should be equal to f naught. So we have already found out a naught. A naught is nothing but f naught. That is what this says. And we can represent, if you like, f naught as f at x naught. So you can call that the 0th divided difference if you like. All right. So we have sorted out a naught. Now let's try to see if we can get a1. Given that we know a naught. Now what happens to this term when x is equal to x1? When x is equal to x1, P2 at x is equal to x1 is going to be equal to f1. We have discussed this already. Now when you come to this representation, P2 at x1 is going to be equal to these first two terms with x is equal to x1. Because when x is equal to x1, this term will be 0, the next term will be 0, this term will be 0, everything will be 0. What survives is the first two terms of this representation. So P2 at x1 is going to be equal to a naught plus a1. X is x1, right? x1 minus x naught. So this is P2 at x1 from this representation of P and x. So these two should be equal. This gives you f1. The Lagrange polynomial gives you f1. This way of representing the polynomial gives you a naught plus a1 times x minus x naught. Therefore, a naught plus a1 x1 minus x naught should be equal to f1. I'm equating the right hand sides of these two expressions because the left hand sides are the same. So we are going to get a1 x1 minus x naught is equal to f1 minus a naught. So this a naught goes to the other side. So you're going to get f1 minus a naught, and therefore a1 is going to be equal to f1 minus a naught divided by x1 minus x naught. And we already know that a naught is nothing but f naught. So a1 is going to be equal to f1 minus f naught by x1 minus x naught. This pattern sounds familiar. This is nothing but the first divided difference involving x naught and x1. That is exactly what is this. That is why we introduced that concept and that notation. Therefore, a1 is nothing but the first divided difference involving x naught and x1. So we have found out a1. So from the data table, we can read out a naught as f naught, the value of f corresponding to x is equal to x naught. Then a1 is going to be equal to the first divided difference involving x naught and x1. So this is nothing but f1 minus f naught by x1 minus x naught. So we take f1 value from the table, we take f naught value from the table, same x1 and x naught from the table, and we can easily compute this ratio, and that is nothing but a1. Now when you come to finding out A2, this representation for P2x at x is equal to x2 is going to give us F2. So P2 at x is equal to x2 is going to give F2. What is this going to give? This is going to give A0 plus A1 x2 minus x0, because we are at x is equal to x2 now, plus A2 x2 minus x0 times x2 minus x1. The other terms will be 0 at x is equal to x2. And we are talking about only P2 of x here. And therefore, you should stop after this term, the second term. All right, so this is what we get for P2 of x at x is equal to x2. So this should equal this. And we know that A0 is nothing but F0. A1 is nothing but F x0 x1, the first divided difference. So that is another information we have. So we can equate the right hand side of like this to this F2 and then do some algebra. So when you do that, you can see that A2 is going to be equal to F x1 comma x2 minus F x0 comma x1 divided by x2 minus x0, which is nothing but the second divided difference involving x0, x1 and x2. If you proceed in the same manner and with a little patience and a little bit of careful work, we can show in general an, the coefficient of the last term, will turn out to be the nth order divided difference. So this is second order divided difference. This is first order divided difference. So this will be nth order divided difference. So what we are trying to say here is the coefficients of this polynomial are exactly the same as the divided differences. A0 is going to be equal to the 0th order divided difference involving x0. So it is going to be f of x0, which is f0. A1 is going to be the first order divided difference involving x0 and x1. A2 is going to be the second order divided difference involving x0, x1 and x2, and so on. And an is going to be the nth order divided difference involving x0, x1, x2 all the way till xn. So that is this way of finding out the coefficients of this polynomial in terms of the divided differences. So if you wanted to know how to derive this, what I've done is I have done the algebra in these two slides. What I do is I take this expression and then I express A2 as a function of, after a little bit of algebra, using all the basic definitions, nothing complex about it. I'm able to show that A2 is equal to this expression. Then what I did was I took the expression for the second divided difference and expressed it in terms of the first divided difference using the definitions given, and expanded these first divided differences to get into this form. Then I took this last term and then I processed it, and then I brought that to this particular form. So this term was shown equal to this term, and then what I did was I said f x0, x1, x2, the second divided difference, is going to be this term plus this term minus this term, right? Because you have a minus sign here, and this was simplified to this. So that is what I'm using here. So I was able to show the second divided difference is equal to this, which exactly matched with my simplification of this expression for A2 from this equation. So I was able to come from both sides and show that A2 is nothing but the second divided difference. Now let's look at this particular problem, which I just touched upon at the beginning of this presentation. So we have 4 data points, as you can see here, unequally spaced, right? The spacing between the x measurements is not the same. So it's 0.2 here, it's 0.3 here, and it's 0.1 here. So the Lagrange polynomial idea can be used for this system. So let's go about constructing the interpolating polynomial. You can go for a third order interpolating polynomial because we have 4 data points. We have x0, x1, x2 and x3. So n is equal to 3. So we can go for a third order interpolating polynomial. So this is how I can construct the divided differences. So starting from here, I can find out the divided difference between these two data points. So I'm going to get f x0 x1 as f1 minus f0 divided by x1 minus x0. So that will give me f x0 x1. I can use these two data points to get f x1 x2. I can use these two data points to get f x2 comma x3. So when I do that, I get these three numbers for these three first divided differences. Now, using these two, I can get the second divided difference because f x0, x1, x2 is nothing but f x1, x2 minus f x0, x1 divided by x2 minus x0. So if I want to get this value, I'm going to do 5.49, which is f x1 comma x2 minus f x0 x1, that is 3.64, divided by x2 minus x0. What is x2 here? x2 is 1.5 and x0 is 1. So 1.5 minus 1. So that is going to be 5, 1.85 divided by 0.5, which is going to be 3.7. And that's what you see here. Likewise, you can compute the second divided difference involving data points x1, x2 and x3, right? So that will be this minus this divided by x3 minus x1. So 7.21 minus 5.49 divided by what is x3 minus x1? x3 is 1.6, x1 is 1.2. So x3 minus x1 is going to be 0.4. So if you take 7.21 minus 5.49, that is going to be 2 and 7 and 1. 1.72 divided by 0.4, which is going to be 17.2 divided by 4, which is going to be 4.3. And that's what you see here. And finally, the third divided difference is going to be 4.3 minus 3.7, which is going to be 0.6, divided by x3 minus x0. x3 is 1.6, x0 is 1. Therefore, x3 minus x0 is 0.6. So the third divided difference is going to be 0.6 by 0.6, which is equal to 1. So we have got all the divided differences here. Therefore, I can write the interpolating polynomial as a naught, which is going to be equal to f naught. What is f naught here? F naught is 1. So therefore, we have this term 1 plus a1. a1 is the first divided difference involving x0 and x1. So 3.64 multiplied by x minus 1, x minus x0. So x minus 1 because x0 is 1. Then plus the second divided difference involving x0, x1 and x2 because a2 we saw was equal to the second divided difference involving x0, x1 and x2. Therefore, this is the second divided difference involving x0, x1 and x2. So we have to take that one. This is also a second divided difference, but that is not a2. This is a2. So 3.7 x minus x0, so x minus 1 multiplied by x minus x1. x1 is 1.2. Therefore, this term makes sense. Then the third divided difference, the value is 1. That multiplied by x minus x0, x minus x1, x minus x2. x2 is 1.5. So this is the interpolating polynomial of order 3 that will pass through all the 4 data points. You can use a similar idea to find out P2x that passes through only the first 3 points. You can readily take it from this table. That means you stop right here. If you're looking for the second order polynomial passing through the last 3 data points, x1, x2 and x3, what would it be? Think about it. I'll stop here and we'll meet you in another video. Thank you.